Hi students, welcome to Inside Physics. I am Srinivas. Today we will see one topic in quantum mechanics, that is de Broglie hypothesis. Okay, de Broglie mentioned something about matter waves. So we will see the concept of de Broglie hypothesis. Okay. So for that just we will take some introduction towards quantum mechanics before going to de Broglie hypothesis. See, in 1925, de Broglie proposed the concept of matter waves with microparticles. Okay, we know that light behave as a wave and a particle, at sometimes as wave and at sometimes as particle. This same theory de Broglie applied to microparticles, and the waves associated with those microparticles are called de Broglie waves. Okay. See, these de Broglie waves are associated with microbodies and microparticles. Okay. Actually, the quantum mechanics is the combination of idea of quantization and idea of wave particle theory. So this combination has developed the quantum mechanics. Okay. See, after that, Heisenberg in 1926 has developed his uncertainty principle and applied it to normal particle structure as a measurement of coordinates, energy and momentum. So later he applied these coordinate and energy momentum to microparticles also. He said that only the quantization should be to the observable particles only. Okay. After that, Schrodinger has developed a differential equation for wave function, and he paved the way for wave mechanics. Priorly, Heisenberg has developed a matrix mechanics which is mostly on observable elements only. But after that, Schrodinger, after developing the differential equation for wave function, the wave mechanics is developed and the matter waves are considered mostly as a mental picture rather than a real one. Okay. So this is a brief introduction of wave mechanics. So a combination of matrix mechanics and wave mechanics is proposed by Dirac, scientist called Dirac. So after that, Max Born, a scientist, proposed the probability theory of finding the matter waves. Okay, this is a structure how the idea of wave mechanics is developed. See, the proposal of Schrodinger wave equation has paved the way for wave mechanics, and the classical way is ending and the wave mechanics is started at that point. Okay. And after that, see, these matter waves, actually called de Broglie waves, are considered as not as normal waves. Okay, we cannot detect them as normally. They are not actually a three-dimensional sound waves like structure. They are mostly a probability waves. Okay, now we see the de Broglie hypothesis. De Broglie hypothesis. Actually, de Broglie applied the wave particle duality of light, which is applicable to light waves. That is applied to microparticles also. He said that when the light is acting at some time as a particle and at other times as a wave, Similarly, the microparticles like electron will act as waves also, at sometimes as a wave also. So this is the actually de Broglie hypothesis. Okay. So here he mentioned some formula to interconnect the wavelength and momentum of the microparticles when they are in motion. He said that they are related as lambda is equal to h by p. Lambda is equal to h by p, where lambda is the wavelength associated with matter waves and h is Planck's constant, p is momentum of the microparticle. Okay. So here the momentum is, we know p is equal to mass into velocity. So in this way he proposed that the wave particle duality can be applied to all microparticles. Okay. So now what is the actually the wavelength of matter waves of as proposed by de Broglie? We will see the wavelength of matter waves. Wavelength of matter waves. So matter waves are also called de Broglie waves, which are associated with every moving microparticle. See here, we know that photons will move with velocity of light. Every photon is associated with a wave which is called an electromagnetic wave. So in this way, for photon, we can write the momentum as proposed by de Broglie by this equation. Momentum of the photon is equal to h by c, where c is velocity of light. Sorry, e, not h, e by c. This is energy of photon and velocity of light. So that we can write E is equal to h nu by c. We know that the energy relation E is equal to h nu. By that I written E is equal to h nu by c. So by this we can write as nu by c, we know that is lambda. So from momentum we have taken E by c and we are given this formula. So by this we can write P is equal to h by lambda. That implies lambda is equal to h by p. This is the relation given by de Broglie for the waves associated with microparticles and their momentum. Okay. So here we can say that whenever the momentum is high, the wavelength will be low, right? Here we can write that, see, E and P, E comma P are related to energy and momentum are related to particle structures, and nu comma lambda, these two are related to waves. These related to particles and these two are related to waves. And he derived two equations which are interrelated and they are connecting particles and waves. We will see how they will connect the particle and wave structures. See, here we can write E is equal to h nu and lambda is equal to h by p. So these two equations will be connecting particles and waves. So these are the two things which are related to particle, and these frequency and wavelength, nu is frequency, lambda is wavelength, are related to waves. So in this way de Broglie proposed the wavelength of matter waves in his way. Okay. So Here in from this lambda is equal to h by mv. From this equation, we can say when the mass of the particle is very low, right, the wavelength associated will be high. And for a bigger objects where the mass is too high, so the lambda will become very low and we cannot detect the waves also, right. So see, if lambda, we see two conditions here. If lambda tends to infinity, here if lambda tends to infinity, v becomes 0, right. If lambda tends to infinity, v becomes 0. So here what we can say is the matter waves associated with microparticles are when the microparticles are moving only, if they are having some velocity only. Okay, the stationary microparticles will not have any kind of waves associated with them. Okay, and the second thing I have already told you, when the mass of the moving particle is very less, then the associated wavelength will be high. So for microparticles like electron, proton, neutron, obviously the mass will be very low. So for higher objects, for bigger objects, we know the mass will be very big. In this case, the lambda will be very less and we cannot detect the waves also. This is dependent dependent on m. Okay. So these are the derivations from these equations. Okay. So if photon we consider sometimes as a particle, at times as a wave. So the photon is associated with some electromagnetic waves. I already told you, and the electromagnetic waves associated just like with the photon, and the microparticles are also having some waves associated with them. So they are actually a probability waves, they are not actually a three-dimensional reality waves, okay, as proposed by the Born. So now next we see the wavelength associated with an accelerated charged particle. An accelerated particle. Wavelength associated with an accelerated particle. If we suppose that an electron is accelerated through some potential difference V, now the wavelength associated with that electron when it is accelerated through a potential difference V, it is given by the it is given as the kinetic energy will be half mv square is equal to EV. The kinetic energy associated with an accelerated electron through a potential difference is V. So by this we can write that half mv square is equal to EV, that implies V square is equal to EV by 2 EV by m, right, 2 EV by m. So V is equal to root of 2 EV by m. So this is the velocity of the electron which is accelerated through some potential difference V. So we know that wavelength associated with that electron is h by p. So here we can write p is equal to mv. In place of v we put this one. Right. So here we can write this one as h by root of 2 ev m. This m we can take it as root m into root m, and we can write this equation as this one. So this lambda which is associated with a charged electron is given by this equation. Okay, and we will see next the wavelength associated with, now we have seen that an accelerated particle. Okay, next we will see the wavelength associated with the particles in thermal equilibrium. Wavelength associated with particles in thermal equilibrium. So before going to this one, the wavelength associated with particles in thermal equilibrium, we will see how the wavelength will be in terms of kinetic energy. We will see how the wavelength of matter waves in terms of kinetic energy, right? See, we know that kinetic energy is equal to p square by 2m, right? We know that kinetic energy is equal to p square by 2m, that is half mv square is equal to p square by 2m. So here what is p actually? H by p. So here the this will be kinetic energy is equal to p square by 2m. That implies p is equal to 2m into kinetic energy, right? Root of 2m into kinetic energy. So here in terms of kinetic energy we can take the wavelength associated with matter wave as h by root of 2m into kinetic energy. So with this relation we will derive the wavelength associated with particles in thermal equilibrium. Actually, when the particles are in thermal equilibrium, the kinetic energy of the particles will become, from thermodynamics we know that 3 by 2 kT, right? Kinetic energy is equal to 3 by 2 kT. When the particles are in thermal equilibrium, the kinetic energy will become that. The kinetic energy we put in this equation. So this becomes root of 2m into kinetic energy 3 by 2 kT, right? So 2 gets will gets cancelled. So this we can write it as 2 kTm. So here we have seen the wavelength associated with the particle when the particle is accelerated, and after that we have seen the wavelength in terms of kinetic energy. After that we have derived the wavelength associated with the particles in thermal equilibrium, and the equation looks like this. So in this way de Broglie proposed his wave particle duality and the associated matter waves thereby, and he successfully able to tell the wave particle duality, and this is taken from the light waves and is applied to microparticles. So here the main concept is actually the wave mechanics has taken over from classical mechanics, where the classical mechanics could not explain the behavior of a particle when it is behaving like a wave. Classical mechanics can explain a particle when it is behaving like a particle. We can calculate the energy levels, momentum and coordinates. But when the particle is associated with a wave, that means when it is behaving like a wave, the classical mechanics exactly could not give the details of the wave picture of the microparticles. So the de Broglie hypothesis has given actually a good clarity about wave mechanics. Okay, this is about de Broglie hypothesis. In the next class we will see some more topics in wave mechanics.